So welcome back. I think the last thing we were dealing with were kind of properties or attributes of communities. Right, numbers that we can use somehow to quantify something about the community. The first property or index we had was this notion of species richness. There should be a certain number of species associated with that community, and this gives us a way to compare between communities. Which community is more speciose? That would be the one with the highest species richness. Talked a little bit about how we could estimate species richness in communities where species are either hard to find or the community itself is very large and intractable. Then we talked a little bit about abundance measures, dominance, density, frequency, and then keep in mind what makes it a property of a community is those relative measures, relative density, because we're considering one species relative to everybody else, relative dominance, relative frequency. Now what we're going to do is basically combine the first two properties, richness and abundance, and kind of smoosh it all together to come up with this measure we call diversity. So species diversity is an index that incorporates both richness and relative abundance of species. And the most common abundance measure to use would be a relative density value. But for some species, and I mentioned this before, density really doesn't make a whole lot of sense. It might be more informative to use some measure of dominance. So if I'm looking at a coral community, a group of corals on a reef, the corals take up space and they take up different amounts of space. So it might make sense to use dominance measures in my species diversity measure rather than density. We're going to take the easy way out and develop species diversity measures using density, but I just wanted to mention that it can be done for species where dominance is much more informative. Okay? Now, like everything else in ecology, there are 50 different ways to do exactly the same thing. So there are lots of species diversity indices. There are lots of them. Probably these different types of indexes developed because for some communities it makes more sense to think about them in one way, whereas other communities in another way. For example, a community of plankton in Presque Isle Bay probably requires a slightly different species diversity index than, say, the population of mammals in Erie Bluff State Park. There are different ways to measure how many individuals I have of each species, and that's going to affect my index, right? The confidence I have in my ability to estimate the number of individuals of each species directly affects my confidence in my index. And there are some mathematical approaches that have been developed to deal with these uncertainties. We're going to talk about two different ones. The first one is called the Shannon Index. You'll also see it referred to as the Shannon Wiener Index. And God help us, it's also called the Shannon Weaver Index, right? And you thought MCB language was all screwed up. And also Shannon, this is the last name. Shannon's a guy from the 50s. But this was Shannon's attempt to develop an index of species diversity. All right, so the index itself is abbreviated as H prime. It's probably the most commonly used one. It's pretty robust for a lot of different community types. It's also pretty easy to calculate. In the days before spreadsheets, it was easy to calculate. In the days with spreadsheets, it's pretty easy to calculate. So basically what this measure is the sum of abundance proportions for each species multiplied times the natural log of that same value. The proportion here is the abundance of species 1 divided by the total abundance in the community. So this is total, this is for species 1. So if we're doing density measures, like I said we would, this would be the number of individuals of species 1 divided by the total number of individuals in the community. And then we would multiply that times the natural log of that same proportion. We would do that for species 1, and we would do the same thing for species 2, species 3, etc., 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 etc. Until we finished all the species, then we would sum that up and come up with this value H prime. Now, not shown in this calculation, I think I probably forgot to put it in there. Sorry about that, but because we're taking the natural log of proportions, the natural log of proportions turns into negative values. So we're going to multiply the sum of everything by -1. That will put the scale in the proper direction. I just thought for a second about pH values, right? When we calculate out pH, it's the negative log of the concentration of hydrogen ions. The log returns these negative values, so we kick that negative into the equation to get us back into positive land. Most people don't like to deal with negative numbers. They don't make a whole lot of sense, right? -40 is a smaller number than -30. That's not very comfortable. So we employ these tricks to try to bring us back into what I would call positive land. And that's what this is an attempt to do. It also has the added benefit of making it so that large values of H prime indicate high species diversity, whereas low values of H prime equals small species diversity or low species diversity. All right, so I have some data here. I pulled this up from a textbook, and then when I ran through the calculations, I promptly regretted it because I found a whole bunch of errors within the table itself. The first error should be pretty obvious as we go through. The next error is in the calculation of a different index that we'll cover in a second. But here we have 3 community types: community A, community B, community C. We're keeping track of 5 species in each of these 3 communities. And notice in community A, 3, 4, and 5 don't exist. It's just a community composed of 2 species, 1 and 2. And therefore the species richness of that community should be 2. Okay, all right, let's go ahead and work through a couple of these calculations. So N1 and N2, that's the number of individuals within each of the 2 species. Just so happens that in community A, they're both the same value. That would mean that the overall abundance or overall number of individuals would be 20. So this calculation would run as 10 over 20 times the natural log of 10 over 20 plus the same thing again because the abundances are the same. So I could just put a little 2 in front there. That would mean we'd be at 2 times 0.5 times the natural log of 0.5. Okay, they've gone ahead and done that calculation for us. the only thing I'd add is that they're incorporating the negatives as part of this calculation, not moving it to the front as I've done. It doesn't matter mathematically. So therefore, their calculation for 2 times 0.5 times the log of 0.5 would be 0.35 plus 0.35 would equal 0.7. And notice that they did something incorrect as well. I just noticed they've rounded in this column instead of carrying everything forward to the end and rounding at the end. Based on their math here, it would be a 0.7, but it looks like with the carrying through of the calculations, you're at a 0.69. Okay? Okay, let's take a look at the second community here. This community has 4 individuals for each of the 5 species. So again, each of these calculations will be the same. So this would set up as 5. I'm going to do that calculation 5 times for each of the 5 species. 4 over 20 times the natural log of 4 over 20. It looks like when you sum that up, you get 4, 8, 10, 1 on 2 is 1.60, and again, it looks like they have a rounding issue. Okay, 1.6. So notice that comparing community A to community B, community A has lower richness, community B has higher richness. Community A, higher abundances, community B, lower abundances, even though the abundance overall is the same. Okay? So in other words, if the abundance values are kept the same, but species richness is increased, the Shannon Index will increase. So the difference between these two communities is simply an increase in the number of species richness. Increase in richness, you get a corresponding increase in species diversity if the abundances are kept the same. Notice also that in both communities, there are equal numbers of the species, which means the evenness is kept the same as well. Okay? The evenness is kept the same. And I can't remember, because it's been a while since I did the other lecture, I can't remember if I mentioned evenness to you, so let me go ahead and do that just in case I didn't. But if you remember, we lined up all of the species from from high abundance over here to low abundance, and put the abundance value on the y-axis, that we had a relationship that looked kind of like this. And my point was, many communities have this kind of a shape to it. We called it a J-curve. And this shape exemplifies kind of temperate regions where there tends to be one or a few dominant species, ones that are everywhere, and then the rest of the species are at pretty low relative density compared to everybody else. On the other hand, if we did the same thing, species, wait, that's terrible. Species, high to low again with abundance here. Tropical communities, on the other hand, tend to look like this. The community is composed of a lot of species in equal abundance relative to each other. Temperate zones, low evenness, and tropics, high evenness. Okay? We may have some time here at the end to talk about why there might be higher evenness in the tropics and corresponding high species diversity values in the tropics. We'll see if we've got time to go through some of that. But in any event, in our plot here, that's what they mean here. This community would have high evenness, and so would this one. So if evenness stays the same, the relative density values are staying the same for each species. We change the richness, we increase the species diversity. With this last community, we would have 18 over 19, 20, 21, 22 times 18, sorry, log of 18 over 22 plus 4 species that are 1 over 22 times the natural log of 1 over 22. It looks like when we add all that together, that gives us a value of 0.78. So here, richness is the same between these two communities, but we lowered the evenness and got a corresponding decrease in species diversity. So my point here is that species diversity values are affected both by evenness, which is how equal the relative densities are with the species, but it's also affected by species richness. Okay? So that's the Shannon Index. The second index here is called Simpson's Index. And just to make things really confusing, there are a few different ways to calculate out Simpson's Index, neither of which is done correctly on this figure. We're going to do it one particular way. So the index itself, we're going to report as 1 minus lambda, because we don't use lambda for any other variables in ecology, right? Lambda is supposed to represent population growth. Here it is showing up in a community measure. Kind of like R is used all the time in ecology as well, right? Intrinsic rate of increase, net replacement rate, right? Percent of variation explained in the Y by the variation in the X variable. And then this value is referred to as D. We have to do this because, as you'll see, if we don't do that, the scale runs in the wrong direction. Low D values would indicate high species diversity. High D values would indicate low